Uranus and Neptune are part of a fascinating group of planets known as ice giants. Unlike their gas giant counterparts, such as Jupiter and Saturn, these two worlds are composed mostly of water, ammonia, and methane in forms that are hard to imagine. Their interiors are subjected to crushing pressures that can reach millions of times that of Earth's atmosphere, while temperatures soar to thousands of degrees Kelvin. It's within these extreme conditions that something extraordinary happens. Methane, the main component in their atmospheres, starts to break apart, releasing pure carbon atoms. These free carbon atoms don't just float around, they begin to crystallize under immense pressure, eventually turning into diamonds. This isn't just theoretical. Laboratory experiments designed to simulate the conditions on Uranus and Neptune have shown that when hydrocarbons are subjected to intense pressure and heat, tiny diamonds can form. These experiments back up the models scientists have been developing since the 1980s, suggesting that both planets could be constantly producing diamonds deep inside their cores. Once formed, the diamonds are incredibly dense compared to their surroundings. Because of this, they slowly sink toward the planet's cores, in what can only be described as a diamond rain. Over millions of years, these diamonds could accumulate, growing larger as they descend. In fact, they might even reach sizes of millimeters or centimeters before they settle deep within the planetary interior. This process is thought to play a crucial role in the planet's internal energy dynamics, possibly even influencing their magnetic fields. Uranus and Neptune both have magnetic fields that are tilted and offset in strange ways compared to Earth's or Jupiter's, which have relatively symmetrical dipole fields. One theory is that this irregularity is caused by the uneven distribution of mass in the planet's interiors, influenced by the movements of heavy diamond particles. As these diamonds sink, they might disrupt the convection currents within the planet's mantles, contributing to the observed magnetic anomalies. In Neptune's case, this process could also be contributing to the planet's unique ability to emit more heat than it receives from the Sun. Uranus, however, is a bit of a mystery. It doesn't release as much heat as Neptune, and scientists still aren't entirely sure why. The differences between the two planets could be tied to how deeply diamonds form and sink within their interiors. Understanding the way these materials move through the planet's mantles is crucial to unraveling this mystery. Scientists believe that the region where diamonds form lies in the carbon-rich layers just above the rocky cores of these planets, and below the hydrogen and helium-dominated atmospheres. The behavior of these layers, as well as the way they transition from one phase to another due to changes in temperature and chemical composition, is a key area of interest. Future missions that involve seismic or magnetic mapping could provide the data needed to confirm these theories. At present, no mission is dedicated to exploring the insides of Uranus or Neptune, but interest in these ice giants has surged, especially after the successes of NASA's New Horizons and Juno missions. NASA, along with the European Space Agency, ESA, has already proposed missions that would involve orbiters and atmospheric probes. These spacecraft would carry instruments capable of measuring gravitational anomalies and detecting infrared signatures. Still, directly confirming the existence of diamond rain would require technologies and techniques that are currently beyond our reach. This research highlights how important high-pressure chemistry is to understanding planetary science. The conditions inside ice giants can't be recreated on Earth, except in highly specialized laboratories. These extreme environments allow scientists to test physical laws in ways that would be impossible in more familiar conditions. The findings not only expand our knowledge of how planets work, but also contribute to advances in material science and condensed matter physics. The implications for astrophysics and industrial research are vast. While the diamonds raining on Uranus and Neptune are beyond our reach for mining, their formation is scientifically invaluable. They provide a stunning example of how extreme environments can produce unexpected and unique phenomena. The presence of solid carbon in the form of diamonds challenges the traditional understanding of planetary interiors. Once thought to be relatively simple, ice giants like Uranus and Neptune are now recognized as complex and dynamic worlds. They represent one of the most exciting frontiers in planetary science today. 2WWA 7b is an exoplanet located about 34 light-years away, orbiting a star in the constellation Hydra. This planet, still young at just 10 million years old, is an exciting discovery in the field of exoplanet research. Its heat, left over from its formation, made it detectable by the James Webb Space Telescope, particularly in the infrared range. The planet's mass is similar to Saturn's, placing it among the lighter exoplanets that have been directly imaged. What makes this discovery remarkable is that before the Webb telescope, scientists couldn't capture images of planets this small in such detail. With the help of the MRE mid-infrared instrument, aboard Webb, 2WWA-7b was captured in high definition, blocking out the light from its parent star using a coronagraph. This technique is key to isolating the planet's image in the glare of its star, allowing us to see it clearly for the first time. The imaging of TWWA-7b doesn't stop with just the planet itself. The debris disk surrounding the star was also captured in stunning detail. This disk, made up of gas, dust, and ice, shows signs of interaction with the planet, possibly due to gravitational forces. These interactions give us a window into how planets like TWWA-7b shape their environment, offering insights into the early development of planetary systems. The spectral data collected from the planet also provided a wealth of information. It revealed the presence of methane and water vapor in the planet's atmosphere, common compounds in gas giants like Saturn. The atmosphere appears to be hydrogen-rich, which aligns with models of young exoplanets similar to Saturn. These findings offer a fresh perspective on the atmospheric chemistry of planets in this mass and temperature range, positioning TWWA-7b as a prime example for studying young exoplanets. The host star of 2WWA-7b, an M-type red dwarf, is one of the most common types of stars in our galaxy. These stars are known for their long lifespans and are frequent hosts of compact planetary systems. However, 2WWA-7b's relatively wide orbit around its star stands out. This unusual distance could be a sign of migration or instability in the early stages of the system, offering a fascinating area of study for astronomers. This breakthrough also highlights the growing potential of mid-infrared direct imaging. Before Webb, planets like TWWA-7b, with lower thermal emissions, were nearly impossible to study directly. Now, thanks to Webb, we can observe these faint exoplanets, opening up new possibilities for the study of planets in thermal emission. TWWA-7b is now part of an exclusive group of exoplanets that have been directly imaged in this way, paving the path for more discoveries. As a relatively cool exoplanet, TWWA-7b represents the lower boundary of direct imaging capabilities. Its proximity and youth make it an ideal target for long-term monitoring. By tracking the planet's orbital movements and observing changes in its debris disk, astronomers can refine their models and estimate the planet's mass with more precision. Further observations will also give us clues about the evolution of the disk and possibly point to hidden companions within the system. This successful imaging of TWWA-7b opens the door to even more exciting discoveries in the future. As technology advances, missions may begin to detect Earth-sized planets in reflected light, pushing the boundaries of what we can learn about distant worlds. The data gathered from TWWA-7b is a crucial step forward in the development of next-generation tools like coronagraphs and stars Hades, which will be essential for studying exoplanets in more detail. 2WWA-7b's image and spectrum provide an unprecedented glimpse into the formation and architecture of a young planetary system. The observation proves that even planets with low thermal emissions can be studied in great detail, validating both engineering innovations and theoretical predictions. The findings expand the catalogue of directly observed exoplanets and pave the way for deeper exploration into the diversity of planetary systems in the universe. To confirm the findings from 2WWA-7b, additional observations are planned. Independent spectral verification is crucial to ensure that the data isn't distorted by artifacts or noise. Future observation cycles will focus on the same molecular bands, and if the detection of dimethyl sulfide DMS is confirmed, it will be a groundbreaking achievement in exoplanet science. DMS is a strong candidate for a biosignature, and its discovery would represent the first potential sign of life beyond our solar system. This would not only shape future telescope missions, but also redefine how we prioritize and select planets for atmospheric research. K218b, the planet under study, would then become a key target for missions focused on atmospheric characterization. The data we've gathered from K218b is already influencing new criteria for identifying planets with potential habitability. This world has introduced an entirely new category of habitability. It challenges the traditional concept of Earth-like exoplanets and expands the scope of astrobiology by suggesting that life could exist in warm, hydrogen-rich atmospheres above vast, deep oceans. This discovery highlights how diverse potentially life-supporting environments can be and underlines the complexity of planets outside our solar system. Ongoing studies of K218b will refine models of chemical equilibrium and biosignature detection, as well as help us better understand how atmospheres retain these essential compounds. With each new observation, we come closer to deciphering the conditions that could support life in distant worlds. Moving further into the outer reaches of our solar system, Pluto, once considered the ninth planet, has revealed unexpected geological activity. Data collected by NASA's New Horizons mission in 2015 showed that Pluto's surface is far more dynamic than previously thought. A particularly intriguing feature is the Sputnik Planitia Basin, a large nitrogen ice plain that's central to models of Pluto's internal structure. Gravitational anomalies observed in this region suggest that there may be a liquid layer beneath the surface, challenging the old notion of Pluto as a frozen, inert world. Thermal and gravitational models have further supported this hypothesis, indicating the presence of a subsurface ocean beneath Pluto's icy crust. This ocean is likely a mix of water and ammonia, or other antifreeze compounds that lower the freezing point, allowing liquid water to exist at extremely low temperatures. The heat from radioactive decay inside Pluto may be enough to keep this ocean from freezing, even beneath hundreds of kilometers of solid ice. Evidence for this ocean can also be found in Pluto's shape and rotation. The alignment of Sputnik Planitia with Pluto's tidal axis suggests that the basin has shifted over time, which would only be possible if Pluto's crust were decoupled from a liquid layer underneath. This reorientation supports the idea of a subsurface ocean that allows for such movement. Tectonic features visible on Pluto's surface also back up the idea of an active, partially molten interior. Large faults and extension fractures indicate that the surface has been stretched, likely due to the freezing and slow expansion of the underlying ocean. As water turns into ice, it expands, putting pressure on the crust and creating stress fractures. These surface features suggest that Pluto has experienced geological activity relatively recently. Additional support for the subsurface ocean theory comes from the planet's relatively youthful surface. Sputnik Planitia has very few craters, which suggests that the surface is less than 10 million years old. This points to active resurfacing processes that could involve convection within the nitrogen ice or exchanges between the ocean and crust. The planet's varied terrain also hints at multiple geological renewal events over time. Spectral data from New Horizons further supports the ocean hypothesis. Unexpected concentrations of ammonia and other volatile compounds on Pluto's surface suggest that these substances have recently been transported from the interior. Cryovolcanism, where icy volcanoes expel water and other materials, could explain this movement. Although no active eruptions have been observed, thermal models suggest that Pluto's interior cools slowly over long periods, aided by a layer of clathrate hydrates that insulate the ocean beneath. If confirmed, this layer of clathrates could explain why the ocean has remained liquid over billions of years. It may also play a role in the long-term structural evolution of the planet. Future missions could provide more concrete evidence of Pluto's subsurface ocean. Instruments like radar sounders, gravity sensors, and thermal imaging could map the subsurface in greater detail and detect active processes. If cryovolcanism is confirmed, sampling the material from these eruptions would reveal the ocean's chemical makeup. Pluto's potential to harbor a long-lived subsurface ocean would place it among a growing list of ocean worlds, which include moons like Europa, Enceladus, and Titan. These worlds share several key traits: cold surfaces, internal heating, and geochemical activity. Pluto's inclusion in this group broadens our understanding of habitability beyond the traditional habitable zone. Turning to the exoplanetary realm, one of the darkest planets ever discovered, TR2b, is located about 750 light-years away in the constellation Draco. This hot Jupiter, a class of gas giant that orbits extremely close to its host star, was first identified using the transit method. This technique measures the dimming of starlight as a planet passes in front of its star. What makes TR2b especially remarkable is its extremely low albedo. Less than 1% of the light it receives is reflected. This makes it darker than coal or black acrylic paint, absorbing nearly all incoming light. This unprecedented darkness was confirmed by the Kepler Space Telescope, which captured 2b's faint signal. Most planets, including gas giants, reflect at least some light, but TR2b is an outlier. It lacks the reflective ammonia clouds that cover planets like Jupiter, instead possessing a dense, heat-trapping atmosphere. The planet's dayside temperatures exceed 1,100 degrees Celsius, and the lack of reflective clouds may be a result of this intense heat. TR2b's dark atmosphere has significant implications for our understanding of planetary science. It challenges assumptions about cloud formation and radiation absorption, making it a key test case for atmospheric modeling. The planet's almost non-reflective nature enhances its ability to absorb light, which in turn helps researchers study its thermal emissions in the infrared spectrum. These emissions provide insights into the planet's temperature and energy distribution. Despite its extreme darkness, TR2b still emits a faint red glow, detectable only in the infrared. This glow is the result of thermal radiation from its heated atmosphere. Though the planet is invisible in visible light, it remains a valuable target for astronomers using infrared instruments. TR2b's discovery forces scientists to reconsider the range of possible planetary conditions, contributing to the refinement of observational techniques and expanding the classification of gas giants. The discovery of alcohol and other organic molecules in space is a major breakthrough for astrobiology. It supports the idea that the essential building blocks for life might form in the vast expanse of interstellar space. These molecules could eventually be incorporated into comets and planetary systems, possibly helping life emerge on young planets. This concept, known as panspermia, suggests that life's essential components might travel across space, seeding new worlds with the potential for life. What makes this discovery even more significant is the sheer scale of the Sagittarius B2 cloud. Just the amount of ethanol alone, spread across light-years of space, is staggering. While we can't collect this alcohol, its abundance reinforces the idea that organic chemistry is widespread in our galaxy. This shows that complex molecules can form and endure in harsh space environments, challenging the old assumption that life's precursors are rare. The Sagittarius B2 cloud is located near the galactic center, a region filled with stars, black holes, and intense radiation. Despite these extreme conditions, fragile organic molecules manage to survive, proving that organic chemistry can thrive even in such violent environments. This discovery raises the possibility that similar clouds could exist in other galaxies, suggesting that life's building blocks might be distributed throughout the universe. Astronomers are continuing to study Sagittarius Bk2 with the goal of identifying even more complex molecules. The aim is to find potential precursors to RNA, proteins, and other biopolymers, which are key components of life. As new technologies such as high-resolution spectrographs and computational modeling advance, more discoveries are expected. Upcoming radio telescopes are being designed to detect these complex compounds, further expanding our knowledge of the chemical processes that take place in space. The discovery of alcohol and other organics in molecular clouds emphasizes the connection between cosmic and biological chemistry. It strengthens the theory that the building blocks of life may already be scattered across the universe, waiting to come together in the right conditions. Sagittarius B2, with its rich molecular content, provides a glimpse into the early stages of planetary system formation. As detection methods improve, scientists hope to identify even more complex, possibly prebiotic molecules. This region is key to understanding the chemical evolution of the universe, and may offer clues to the origins of life itself. Shifting to a completely different cosmic phenomenon, in the center of the Perseus galaxy cluster lies a supermassive black hole that is producing sound waves in the surrounding gas. First detected by the Chandra X-ray Observatory in 2003, these sound waves appear as ripples in the X-ray emitting hot gas that fills the cluster. These waves have a regular repeating pattern as the black hole essentially vibrates the gas around it. Interestingly, the sound produced by this black hole corresponds to a pitch 57 octaves below middle C. This is the lowest known sound ever recorded in the universe, far below the range of human hearing. These sound waves are not transmitted through space's vacuum, but instead travel through the dense medium of hot plasma within the galaxy cluster. The black hole's activity causes pressure changes in the gas, which generates the acoustic waves. This occurs due to periodic outbursts from the black hole as matter falls into it, releasing energy and inflating bubbles of high-energy particles. These bubbles push against the surrounding gas, creating pressure waves in a form of mechanical feedback that regulates galaxy growth. The sound waves also play a role in heating the surrounding gas, preventing it from cooling too quickly and forming stars at an unusually high rate. This feedback process helps keep star formation in check and demonstrates that black holes influence their environment on an enormous scale. The term black hole hum is a metaphor for this slow, rhythmic process. It provides a unique method for astronomers to study the cosmic environment around black holes. NASA has even released sonifications of the Perseus cluster data, converting the pressure variations into audible sound for public outreach. Beyond providing a captivating experience for the public, these sound waves help astronomers map the physical conditions in the cluster. The amplitude, spacing, and speed of the ripples offer valuable information about the density and temperature of the gas, as well as the history of the black hole's outbursts. This long-term data is difficult to gather through other means, and the Perseus cluster serves as an ideal natural laboratory for studying these phenomena. Similar acoustic activity has been observed in other galaxy clusters, such as the Virgo cluster. However, the Perseus case remains the clearest example of sustained acoustic waves, demonstrating that black holes can shape their environments not only through radiation but also through mechanical energy. This has completely reshaped our understanding of black holes, showing that they are not passive entities, but active forces that shape the ecosystems of galaxies. These new findings are now a key element in cosmological simulations and have opened new methods for studying the dynamics of galaxy clusters. Moving on to black hole theory, we turn to the famous concept of Hawking radiation, first proposed by Stephen Hawking in 1974. According to Hawking, black holes are not entirely black. They emit radiation due to quantum effects near the event horizon. Over time, this radiation causes the black hole to lose mass and energy. The process is incredibly slow for massive black holes, but theoretically it affects all black holes, no matter their size. Heretofore, eviation occurs because of quantum field fluctuations near the event horizon, where particle-antiparticle pairs are constantly being created and annihilated. Occasionally, one particle falls into the black hole and the other escapes, which results in radiation being emitted. This gradual loss of mass is what leads to the slow evaporation of black holes. However, the process is so slow that it would take much longer than the current age of the universe for large black holes to fully evaporate. Smaller black holes, on the other hand, emit more radiation and would evaporate faster. Despite no direct detection of Hawking radiation, it remains one of the most exciting and important predictions of theoretical physics. Its potential detection could bridge the gap between quantum mechanics and general relativity, two pillars of modern physics that have long remained separate. Some laboratory experiments have attempted to simulate similar effects, but detecting Hawking radiation in a black hole remains a major challenge. The idea of evaporating black holes also has significant implications for the future of the universe. As stars burn out and galaxies fade, black holes may be the last remaining energetic objects in the cosmos. Their slow evaporation could be one of the final processes in the universe, potentially leading to the black hole era, where black holes are the only surviving objects in a dark and cold universe. As black holes shrink, their radiation increases, and the emission becomes more intense, potentially culminating in a burst of gamma rays. While this theoretical flash could be detectable in the distant future, no confirmed observations have yet been made. These predictions continue to inspire research into the nature of black holes and their role in the cosmic timeline. Hawking's work has transformed our understanding of black holes, showing that they are dynamic systems with temperature and entropy. Though the concept of Hawking radiation remains unconfirmed, its impact on physics is undeniable. It represents one of the most profound ideas linking the quantum world with the cosmic one, and it continues to shape the future of theoretical research. In 2024, astronomers made a fascinating discovery, a new natural satellite briefly orbiting Earth, named 2024 PT5. These objects, called mini-moons, are much smaller than our moon and typically remain in orbit around Earth for just a short time. Measuring only a few meters in diameter, they are captured by Earth's gravity from asteroid populations near our planet or debris from lunar impacts. 2024 PT5 is one of the clearest examples of such a mini-moon ever documented. The object was detected using wide-field survey telescopes designed to track fast-moving near-Earth objects. Its trajectory fit the pattern of a temporarily captured orbiter, which loops around Earth for a while before escaping into solar orbit. This particular mini-moon was gravitationally bound to Earth for several months. After completing several orbits, it eventually escaped, returning to its orbit around the Sun. The event follows well-established models of mini-moon dynamics, where these objects are temporarily captured through complex three-body interactions involving Earth, the Moon, and the Sun. These orbits are chaotic and unstable, making long-term capture extremely rare. Most mini-moons stay in Earth's orbit for only a few months or up to a couple of years. Because of their small size and rapid movement, detecting these objects can be a challenge. Up until recently, only a handful of mini-moons had been observed. One previous mini-moon, 2006 RH-120, orbited Earth for about 11 months before escaping. The discovery of 2024 PT5 has reignited interest in studying these objects, as they offer unique opportunities to explore the early solar system. Some of these mini-moons might be fragments of the Moon or debris from ancient asteroids. Studying them can give us valuable insights into impact dynamics, orbital resonances, and the complex nature of temporary satellites. 2024 PT5 is particularly interesting because its spectral signature suggests it may have originated from the Moon, possibly ejected during a past impact. If this theory is confirmed, it would not only reinforce the idea that lunar debris can re-enter Earth's orbit, but also provide a direct link between the Moon's surface and temporary satellites. This discovery could explain some high-velocity particles found on Earth, shedding light on the connection between the Moon's history and the objects that briefly join Earth's orbit. Mini-moons also hold great potential for low-cost space missions. Their small size and proximity make them ideal candidates for robotic exploration. Missions to these temporary satellites could test capture techniques for asteroid material, and even serve as test beds for planetary defense strategies. Their short but valuable orbits offer a limited but unique opportunity for study, making mini-moons prime targets for future missions. The discovery of 2024 PT5 has sparked renewed interest in mini-moon detection networks. Ground-based telescopes like Atlas and Pan-STARRS are being optimized to track fast-moving objects like this. These systems scan the sky multiple times a night, allowing astronomers to quickly identify and track transient motion. Advanced algorithms are being developed to filter out noise and quickly confirm the existence of these objects. In addition to ground-based telescopes, space-based observatories could further enhance detection capabilities, particularly infrared telescopes that can pick up dim objects missed by Earth-based instruments. Future missions may even include dedicated mini-moon trackers, dramatically increasing the number of detections. Statistically, Earth captures a mini-moon roughly once every few years. As detection techniques improve, more of these fleeting companions will likely be discovered. Each one presents a rare opportunity to closely study a natural satellite, providing valuable data about the dynamics of our solar neighborhood. These objects, while temporary, represent a unique and exciting class of celestial bodies that may reveal new insights into Earth's gravitational interactions and the broader dynamics of the solar system. Turning our attention to the universe's more extreme objects, neutron stars are among the densest objects known to exist. Formed from the collapsed cores of massive stars after a supernova, neutron stars result from the gravitational collapse of a star that has exhausted its nuclear fuel. These stars typically have masses between 8 and 20 times that of the Sun. After the outer layers are expelled, the core contracts so tightly that protons and electrons merge to form neutrons, creating a dense object made almost entirely of degenerate neutron matter. The result is a neutron star, one of the densest objects in the universe. A typical neutron star has about 1.4 times the mass of the Sun packed into a sphere just about 20 kilometers wide. This gives the star an average density comparable to that of an atomic nucleus. To put it in perspective, a teaspoon of neutron star material would weigh around 1 billion tons on Earth. This incredible density is the result of the extreme compression of matter, where nuclei are pushed so close together that electrons are absorbed into the neutrons. Neutron stars don't have solid surfaces in the usual sense. Instead, they have a thin crust over a liquid interior, made up of neutron-rich fluid. Beneath the crust lies a superfluid core, which may even contain exotic particles such as hyperons or free quarks. Theories suggest that neutron stars could also feature nuclear pasta, a unique phase of matter shaped by competing nuclear forces. These internal structures are inferred through simulations and the study of neutron star oscillations. Many neutron stars emit beams of radiation from their magnetic poles. As the stars spin, these beams sweep across space like a lighthouse, and when they align with Earth, we observe them as pulsars, extremely regular sources of radio waves. Some neutron stars spin hundreds of times per second, with the fastest known pulsar rotating at over 700 times per second. This high-speed rotation demonstrates the extraordinary stability and precision of these stars. Neutron stars also have powerful magnetic fields, up to 1 trillion times stronger than Earth's, and in some cases, these fields can trigger surface quakes and gamma-ray flares. These bursts are among the most energetic events in the universe, offering insights into quantum mechanics in extreme field conditions. Gravitationally, neutron stars create intense curvature in space-time. In binary systems, neutron stars can be used to test general relativity. The orbital decay of these systems, caused by the emission of gravitational waves, matches the predictions made by Einstein's theory. In 2017, LIGO and Virgo detected a neutron star merger, confirming that these stars are significant sources of gravitational waves. The event also produced heavy elements, such as gold and platinum, through the process of kilonova explosions. Neutron stars provide a natural laboratory for testing models of matter under supernuclear densities, bridging astrophysics and nuclear physics. They are crucial for refining our understanding of the strong nuclear force, as measurements of their mass and radius offer valuable insights into the equation of state for dense matter. Observatories like NICER and XMM Newton contribute essential data, and some neutron stars in binary systems even accumulate matter from their companions, triggering thermonuclear explosions on their surfaces. These X-ray bursts help scientists understand the composition and structure of the crust, as well as how heat and matter are transported within the star. Each new observation of a neutron star helps to refine our understanding of stellar evolution, and researchers are increasingly exploring the possibility of hybrid stars, which may contain both a neutron shell and a quark matter core. If confirmed, this would bridge the gap between astrophysics and particle physics, providing evidence for phase transitions in matter under extreme conditions. Future gravitational wave detections may indirectly reveal such hybrid stars, adding a new dimension to our understanding of the universe. GJ 9827d is a fascinating exoplanet that has captured the attention of astronomers. Its unique characteristics are valuable for studying the evolution of planetary atmospheres. The planet's mass and radius suggest that it has a thick gaseous envelope surrounding a rocky core. While it's denser than gas giants, it's still less dense than planets like Earth. Theoretical models suggest that its atmosphere could stretch over tens, if not hundreds of kilometers in thickness. This unusual atmosphere hosts water in a supercritical state, existing in a phase between liquid and gas. As a result, the planet experiences an incredibly dynamic environment. The detection of such an atmosphere on a planet of this size is extraordinary. Most exoplanets with detailed atmospheric data are either massive gas giants or mini-Neptunes. GJ 9827d lies somewhere in between, falling into a gap that makes it hard to observe. The planet's small size and its close proximity to its star complicate atmospheric detection. Thankfully, the James Webb Space Telescope (JWST) helped reveal these atmospheric features by leveraging its powerful infrared capabilities. While the presence of water vapor doesn't necessarily mean the planet is habitable, it does provide crucial insights. GJ 9827. G is too close to its star for liquid water to exist on its surface, if a surface exists at all. However, this discovery challenges prior models that predicted the planet would lose its atmosphere entirely. Instead, the planet's atmosphere manages to survive under intense stellar radiation, proving that even small planets can maintain substantial volatile envelopes. This has significant implications for future research and our understanding of planetary evolution. The findings also offer scientists a unique opportunity to refine mass-radius relationships in planetary science. By comparing the planet's atmospheric composition to its bulk density, researchers can better understand its internal structure. This helps distinguish between rocky planets with thin atmospheres and those with thick, volatile envelopes. Such studies are essential for accurately classifying exoplanets. In 2025, a rare stellar occultation provided new and detailed insights into the atmosphere and ring system of Uranus. A stellar occultation occurs when a planet passes in front of a distant star, briefly blocking its light. This phenomenon allows scientists to study the layers of a planet's atmosphere with remarkable precision. The occultation event was particularly significant for Uranus, revealing new complexities in its atmospheric structure. For the first time, we observed that Uranus's upper atmosphere wasn't uniform, as previously believed. Instead, it displayed multiple temperature inversions, where the temperature actually increased with altitude in certain layers, challenging earlier models of ice giants. These inversions affect wind patterns and cloud formation, adding depth to our understanding of Uranus's dynamic atmosphere. The event also allowed scientists to map the haze layers that envelop the planet, made of hydrocarbons and other compounds formed by photochemical reactions. These hazes scatter sunlight, affecting how we observe the planet. The results from 2025 show that the haze is more layered than we thought, a discovery that will help refine our interpretation of spectral data from the planet. Additionally, the occultation revealed more about Uranus's dark and relatively young ring system. As the planet passed in front of the star, the dimming of light helped scientists measure the thickness and density of its rings. Some of the rings were found to be narrower and denser than previously estimated, providing crucial information to improve models of ring dynamics. This event, the most detailed observation since Voyager 2's flyby in 1986, also helped refine our understanding of Uranus's shape. Subtle shifts in the timing of the star's reappearance across different observatories revealed slight equatorial bulging, offering new insights into the planet's internal mass distribution and rotational dynamics. These observations are helping us model the interior of Uranus, which will be critical for understanding the formation and evolution of ice giants. While stellar occultations are rare, they offer invaluable opportunities to study distant planets with exceptional detail. The 2025 Uranus occultation highlights how such events, when precisely timed and coordinated, can yield rich scientific data. The upcoming Vera-Rubin Observatory will provide even more detailed measurements, further enriching our understanding of planets like Uranus. The Boomerang Nebula, located about 5,000 light-years away in the constellation Centaurus, is one of the coldest naturally occurring objects in the universe. With temperatures reaching just 1 Kelvin, about -272 degrees Celsius, it is colder than the cosmic microwave background radiation, which is around 2.7 Kelvin. The extreme cold in the nebula is caused by the rapid expansion of gas ejected from the dying star at its center. This fast-moving gas cools due to adiabatic expansion, a process similar to how compressed air cools when released. The nebula, which spans nearly a light-year across, emits very little visible light. Instead, most of its emissions are in the radio and microwave bands, which require specialized equipment to detect. Observations from ALMA and other radio telescopes have provided critical data on the velocity and structure of the nebula, helping us understand the dynamics of mass loss during the late stages of stellar evolution. The origin of the nebula's unusual temperature has long been a mystery. Now, models show that the cooling is caused by extremely fast outflows of gas, about 164 kilometers per second, higher than those in typical planetary nebulae. This rapid cooling prevents the nebula from absorbing enough radiation to warm up again, keeping its environment at record low temperatures. However, this ultra-cold phase won't last forever. As the central star evolves into a white dwarf, the surrounding gas will heat up, and the nebula will transition into a more typical planetary nebula. This rare and transient phase offers a unique opportunity to study the chemistry of the nebula. Molecules that would normally break apart in warmer conditions, like complex organic molecules and frozen dust grains, can survive here. These components could seed future star-forming regions, enriching them with the elements needed to form new stars and planets. Astrophysicists use the Boomerang Nebula to test models of stellar wind dynamics. The nebula's asymmetric mass loss, with material ejected more strongly along the poles than at the equator, helps refine our simulations of late stellar evolution. The Boomerang Nebula is an extreme case that anchors one end of the thermal spectrum, challenging traditional observational assumptions. It encourages scientists to reanalyze archived data with improved sensitivity, possibly leading to the discovery of similar phenomena elsewhere in the galaxy. Despite its faint appearance, the Boomerang Nebula is a fascinating subject in the study of dying stars. Its ultra-cold temperatures, rapid expansion, and unique structure make it one of the most intriguing stellar remnants known. It offers a glimpse into the extreme physics of stellar death and highlights how even faint, cold objects can reveal hidden aspects of the universe. Mars, once thought to be a dry and lifeless planet, may still harbor liquid water beneath its surface, albeit in the form of briny solutions. Data from NASA's Mars Reconnaissance Orbiter, MRO, has uncovered recurring dark streaks on Martian slopes known as recurring slope lineae, RSL. These streaks grow during the warmer months and fade when temperatures drop, suggesting the presence of transient liquid flows. The key to this discovery lies in the spectrometer aboard the MRO, which has identified the RSL's composition as salty water. These seasonal flows are believed to be made up of brine water mixed with salts that lower its freezing point. This finding provides compelling evidence that liquid water could still exist on Mars today, albeit in limited quantities and under specific conditions. The discovery of briny water on Mars opens up new possibilities for understanding the planet's potential to support life, past or present. While this water cannot sustain life as we know it on Earth, it provides critical insight into Mars's climate and geology, and it may even serve as a resource for future missions to the Red Planet. As scientists continue to analyze the data, we move closer to uncovering the mysteries of water on Mars, one of the key ingredients for life. For a long time, Mars was thought to be an arid, lifeless world, but recent discoveries are changing that view. New data from NASA's Mars Reconnaissance Orbiter, MRO, suggests that Mars may still harbor liquid water, albeit in briny, transient forms. One of the most intriguing findings is the presence of recurring slope lineae, RSL, dark streaks that appear and change with the seasons. These streaks grow during the warmer months and fade when the temperatures drop, indicating that something is flowing beneath the surface. The key to understanding these streaks lies in the presence of hydrated salts, such as perchlarates. These salts lower the freezing point of water, allowing it to remain liquid even at temperatures far below zero. In Martian conditions, pure water would quickly freeze or evaporate. However, briny water can persist in a metastable liquid state, which helps these streaks appear and disappear each year. These RSLs are typically found on equator-facing slopes, where the sun's warmth is most intense. In these areas, temperatures occasionally rise above -20 degrees Celsius, which, combined with the salts, creates a narrow window for liquid water to exist. Researchers suggest that the water could either come from the atmosphere, which can absorb moisture and produce frost, or from small pockets of subsurface ice. As Mars warms during specific times of the year, this ice may melt, and the resulting brine would flow briefly down the slopes before refreezing. Though the amount of water is small and these flows are brief, the discovery still represents the best evidence we have of liquid water on Mars today. The implications for life are profound. If briny water can exist, It's possible that microbial life could survive in protected niches, similar to Earth's extremophiles found in environments like Antarctica's subglacial lakes. Mars may harbor analogous conditions that could sustain life in small, isolated habitats. The conformation of liquid water, even if it's transient and briny, suggests that Mars is not as dry or geologically inactive as we once thought. This discovery raises new possibilities for astrobiology and the potential for human exploration. However, studying these areas directly is tricky. Planetary protection protocols prevent landers from visiting regions that may harbor liquid water, as there is a risk of contaminating these environments with Earth organisms. As a result, investigations into the RSL sites are complex and carefully regulated. There is still some debate over whether the RSLs are truly water-driven. Some scientists propose that dry granular flows might explain the streaks. However, the presence of hydrated salts strongly supports the theory that liquid water is responsible. Continuous monitoring, new imaging techniques, and spectral data from orbiters will be critical in confirming this theory. Future missions may even use ground-penetrating radar and temperature probes to directly measure subsurface moisture, potentially revealing the true origin of these seasonal flows. These briny flows on Mars are a window into the planet's ongoing hydrological processes. They suggest that Mars has not completely lost its water, and that geological activity might still be at play beneath the surface. With more data, scientists hope to refine our understanding of Mars's present-day conditions and its potential for hosting life. When you think of auroras, you probably picture the mesmerizing lights of the northern and southern skies on Earth. But the auroras on Jupiter and Saturn are far more intense and dynamic. These cosmic light shows are powered by the interaction of charged particles from the solar wind with the planet's powerful magnetic fields. While Earth's auroras are most prominent near the poles, Jupiter and Saturn's auroras are much stronger and can span vast areas of their atmospheres. Jupiter's auroras are the most intense in the solar system, largely due to the planet's immense magnetic field. Unlike Earth, where solar winds primarily drive auroras, Jupiter's moons, especially Io, play a significant role in creating its auroras. Io's volcanic activity ejects particles into space, which become ionized and trapped in Jupiter's magnetosphere. These particles then accelerate along magnetic field lines toward the poles, where they collide with the planet's atmosphere, exciting hydrogen molecules and causing ultraviolet auroras to glow. These auroras on Jupiter are persistent, often visible even without solar storms. Saturn's auroras are also influenced by solar wind and the planet's rapid rotation, but they are somewhat more sensitive to changes in solar activity. Observations from the Cassini spacecraft revealed that Saturn's auroras form ring-like structures that change and shift with the planet's magnetic field. These shifts provide insights into the complex dynamics of Saturn's magnetosphere. Both Jupiter and Saturn's auroras emit energy that far exceeds what we see on Earth. Jupiter's polar auroras are hundreds of times more energetic than those on Earth, releasing energy equivalent to millions of lightning bolts. These displays are not only spectacular to watch, but they also provide critical information about the planet's magnetic fields, atmospheres, and how their interiors interact with their magnetospheres. Jupiter's auroras, in particular, are a valuable tool for studying the planet's ionosphere and thermosphere. The energy emitted during these auroras reveals the composition, density, and energy levels of Jupiter's upper atmospheric layers. Similarly, Saturn's auroras give scientists insights into the interactions between solar winds and the planet's magnetic field. Both planets' auroras can also help scientists monitor space weather, as sudden changes in auroral brightness can signal incoming solar wind shocks. These dazzling light shows not only brighten the skies, but also illuminate the mysteries of the gas giants. By studying these auroras, we're learning more about the complex and dynamic environments of these distant planets. They offer clues into the behavior of charged particles and magnetic fields, providing a unique perspective on the outer solar system. Long-term observations of planetary auroras have revealed fascinating patterns linked to the solar cycle. These observations are crucial for calibrating models that help us understand how a planet's magnetosphere and ionosphere interact. Recent data from NASA's Juno spacecraft, which orbits Jupiter, has taken this understanding to new heights. Juno's ultraviolet and infrared instruments have provided the clearest and most detailed views of Jupiter's auroras yet. These observations have uncovered fine structures in the auroral arcs, including wave-like features and localized flares. However, some of these phenomena remain a mystery, indicating the complexity of the underlying electron dynamics. These new findings continue to challenge existing theoretical models. But auroras aren't just captivating light shows. They are valuable to the field of comparative planetology. By studying how auroras form on different planets, scientists can test theories about magnetic field generation, atmospheric chemistry, and internal heat flow. This knowledge may even extend beyond our own solar system. Exoplanets with magnetic fields could potentially generate aurora-like emissions, making giant planet auroras a key analog for understanding distant worlds. Jupiter's auroras, in particular, reveal the immense scale and complexity of magnetospheric physics. These spectacular light displays are not just visual phenomena, they're physical records of how a planet interacts with the space environment around it. As more missions and telescopes continue to study the outer planets, auroras will remain central to understanding both their internal workings and their external environments. Vesta, one of the largest objects in the asteroid belt, holds some surprising geological features. With a diameter of about 525 kilometers, Vesta is much smaller than Earth's moon, but it boasts some of the tallest mountains in the solar system. The Riana Silvia Basin, a massive impact crater, hosts a central peak that rises roughly 22 kilometers above the surrounding terrain. This peak is comparable to, or even surpasses, the height of Olympus Mons on Mars, when measured relative to the local surface. This central peak was formed about 1 billion years ago, when a massive impact struck Vesta's southern hemisphere. The collision excavated much of the asteroid's surface, and as the material below surged upwards, it formed the towering central peak. This process, known as impact rebound, is common in large craters, but is rarely seen at such a scale on small bodies like Vesta. The low gravity of Vesta has allowed for such extreme topography. Vesta's internal structure, differentiated into a core, mantle, and crust, allowed it to respond to this impact like a planet, forming complex surface features. The Ria Silvia Basin spans around 500 kilometers across, nearly the size of Vesta itself. This large-scale event caused stress across the surface of the asteroid, leaving behind ridges and troughs aligned with the basin. The mountain's height was precisely measured by NASA's Dawn spacecraft, which orbited Vesta in 2011. Using stereo cameras and laser altimeters, Dawn mapped the surface, creating detailed 3D models that revealed the mountain's impressive elevation. Despite its small size, Vesta remains geologically coherent. Its solid, rocky composition has preserved the features of the Ria Silvia Basin, which is otherwise prone to erosion on other planetary bodies. Vesta's lack of atmosphere minimizes the effects of wind and water-based erosion, leaving its surface primarily shaped by impacts. In fact, the collision that created Ria Silvia ejected fragments of Vesta across the asteroid belt. Many of these fragments have been identified as V-type asteroids and meteorites found on Earth, providing physical samples that match Vesta's surface composition. Vesta's mountain formation defies conventional expectations. While mountain building is typically associated with tectonic activity, Vesta's features were formed by impact rebound and the mechanics of its crust. This discovery has reshaped our understanding of what small bodies in the solar system can support. Vesta serves as a bridge between rocky planets and irregular asteroids, offering a glimpse into planetary processes at a smaller scale. Launched in 1977, Voyager 1 has become the farthest human-made object from Earth, now operating beyond the heliosphere. Originally designed as part of NASA's Voyager program to explore the outer planets, Voyager 1 flew past Jupiter and Saturn before heading toward interstellar space. In 2012, it crossed the heliopause, the boundary where the solar wind gives way to the interstellar medium. This moment marked its official entry into a new frontier of space, and Voyager 1 became the first spacecraft to reach this region. The heliosphere is essentially a protective bubble of charged particles that extends out from the Sun. At the edge of this bubble, the environment transitions from the solar wind to the interstellar medium. Voyager 1's instruments detected a sharp increase in galactic cosmic rays and a significant drop in solar particles, signaling its departure from the heliosphere. These data provided the first direct measurements of the interstellar medium and offered invaluable insights into how the Sun interacts with its cosmic surroundings. Even at more than 20 billion kilometers from Earth, Voyager 1 continues to send back valuable scientific data, albeit at a very low bandwidth. The spacecraft is powered by radioisotope thermoelectric generators, which slowly degrade over time. To conserve energy, many of its systems have been shut down, but key instruments such as the plasma wave, magnetic field, and cosmic ray detectors remain operational. Voyager 1 has even discovered persistent low-frequency plasma waves in interstellar space, offering crucial data about the density of the medium. Despite being launched in the 1970s, Voyager 1 remains relevant in modern space exploration. It provides a unique perspective on the solar wind and magnetic field, complementing newer missions like IBEX and the Parker Solar Probe. Its data helps refine models of the heliosphere's shape and structure. Voyager 1 is also a symbol of human curiosity and ingenuity, carrying with it the Golden Record, a message from humanity, including sounds, images, and greetings in multiple languages, intended for any intelligent life that might encounter it. Voyager 1 will continue its journey through the galaxy, eventually passing near the star Gliese 445 in about 40,000 years. It will silently travel the cosmos after its systems shut down, illustrating the vastness of interstellar space. For now, its ongoing motion represents humanity's first step into the galaxy. Although communication with Voyager 1 is a slow process, requiring over 40 hours for a round-trip signal, it remains a testament to the durability of well-designed spacecraft. 55 Cygni, located 41 light-years away in the constellation Cancer, is a super-Earth exoplanet that has drawn significant interest due to its extreme conditions. This planet orbits its parent star in just 18 hours, a revolution speed that results in surface temperatures exceeding 2,000 degrees Celsius. Such heat is unimaginable by Earth standards, making it one of the hottest exoplanets discovered so far. The proximity of 55 Cygni to its star means it experiences intense radiation, which contributes to its blistering temperatures. While its extreme environment makes it unlikely to support life as we know it, studying this planet provides valuable insights into the nature of super-Earths, planets larger than Earth but smaller than Uranus or Neptune. The intense heat and conditions of 55 Cygni make it an important target for studying the upper limits of planetary habitability. Temperatures on this planet soar beyond 2,000 degrees Celsius, and it's twice the size of Earth, with a mass that's about 8 times greater. These extreme conditions, paired with its unique composition, make it a prime candidate for being a carbon-rich world. The idea that this planet could be made of diamond comes from its inferred density and the nature of its star. The star 55 Cygni has a high carbon-to-oxygen ratio, meaning the disk from which this planet formed was likely rich in carbon. If the planet's interior mirrors this composition, it could potentially be made of substantial amounts of crystalline carbon, including diamonds. Models suggest that under the right pressure and carbon abundance, diamond could form deep within the planet's mantle, just as it does deep inside Earth. On Earth, diamonds form beneath immense pressure underground. On 55 Cygni, its stronger gravity and internal heat could replicate, or even exceed, the pressure conditions needed for diamond formation. The planet might have a silicate crust with a carbon-rich mantle that includes diamond and graphite. Telescopes, such as the Spitzer Space Telescope, have observed the planet's dynamic atmosphere, revealing drastic temperature variations on its surface, possibly indicating lava flows or heat transport. There's also evidence suggesting the planet's atmosphere is being stripped away by intense stellar radiation. This complicated environment presents a challenge for modeling its surface and atmosphere accurately. Although the idea of a diamond planet is still theoretical, it's based on solid physics principles. Spectral observations haven't yet provided enough detail to confirm the composition of its interior, but the hypothesis remains fascinating. It expands the known diversity of planets and shows how different stellar environments can lead to very different planet chemistries. A diamond or carbon-rich mantle would affect the planet's physical properties significantly. Diamonds and graphite have different thermal and seismic properties compared to silicates, which would influence internal heat transfer, tectonic activity, and surface behavior. If this planet has a diamond mantle, it could also impact the planet's magnetic field, assuming it has one. These findings challenge our assumptions about planetary habitability and classification. 55 Cancri proves that not all rocky planets are Earth-like. Instead, the planet's composition depends heavily on the star and disk from which it formed. This has implications for how we categorize planets, and it broadens our understanding of exoplanet diversity. The planet's proximity to its star likely results in tidal locking, meaning one side always faces the star while the other remains in constant darkness. This would create extreme temperature differences between its two hemispheres. The day side might be hot enough to sustain a magma ocean, while the night side could allow for atmospheric condensation. These dynamics complicate the planet's potential for habitability and influence the way we observe and study it. Future telescopes, like the James Webb Space Telescope, are set to investigate planets like 55 Cancri e in much more detail. They will study their atmospheres, look for specific molecules, and refine our understanding of their internal structures. If diamond signals are detected, 55 Cancri e would make history as the first confirmed carbon-rich planet. This would represent a monumental breakthrough in exoplanet research. 55 Cancri e represents the kind of exotic planet that forms in extreme conditions, expanding our view of planetary diversity. Whether or not it's truly diamond-rich, the planet offers a glimpse into the alternate chemistries that can exist on worlds outside our solar system. This discovery reshapes our ideas about planetary formation and diversity. In 2002, astronomers embarked on a quest to determine the average color of the universe by compiling light data from over 200,000 galaxies. Their result, which combined all the light from these distant galaxies, turned out to be a pale beige. This color, humorously named cosmic latte, reflects the light from billions of stars and galaxies, and it's a surprisingly neutral shade. The concept came from efforts to better understand galaxy formation and stellar populations. Since stars emit different wavelengths of light depending on their temperature and age, the light from galaxies is a mix of these colors. Younger, hotter stars emit blue light, while older, cooler stars emit red. When averaged across many galaxies, the result is a warm white light. However, the color is slightly shifted because of redshift, an effect that occurs as light stretches when moving away from observers. There was initially a misconception that the universe's average color was turquoise, but this was quickly corrected using more precise models of human color perception. The revised color is a soft beige with a hint of pink, a balance between the blue from younger stars and the red from older ones. This neutral hue, akin to coffee with milk, gives insight into the universe's stellar population. It suggests that galaxies are currently a mix of star-forming regions and older, more passive populations. If the universe had more young stars, the color would shift more towards blue, but as star formation slows, it becomes more red. While the universe may look dark to the naked eye because of vast empty spaces between stars, the average color is an abstraction that helps astronomers understand large-scale stellar demographics. It's a statistical average, not a color you would actually see in the sky. This finding also highlights the challenges of human color perception in astronomy, as much of the data comes from wavelengths we can't see, like infrared or ultraviolet. The cosmic latte serves as more than a curious fact. It's a tool for understanding the evolution of the universe. It offers a snapshot of the current state of star formation, and as the universe ages, the color will continue to change. In the distant future, if the universe endures, it may emit more in the infrared spectrum, marking a shift in the way the universe looks and behaves. While cosmic latte is a whimsical concept, it's built on solid scientific foundations and provides valuable insights into the history and future of the cosmos. The theory about Earth's moon possibly having had a second companion is both speculative and fascinating. This second moon might have influenced the moon's tilt and orbit in ways that are crucial to understanding the early Earth-Moon system. Though the hypothesis remains uncertain, It opens the door to the profound impact that collisions and orbital mechanics can have on shaping planetary systems. Major impacts can create moons, but smaller scale interactions could leave behind subtle geological traces. The uneven surface of the moon, with its towering far-side highlands, could be a lasting record of this vanished companion. Though this hypothetical second moon is long gone, its potential impact could still be seen in the moon's topography. The far side's geological features, particularly its unusual crust and highlands, are important clues that deserve more attention. This idea exemplifies how celestial mechanics and geology work together to explain planetary histories. It reflects the ongoing evolution of our understanding of Earth's closest neighbor and the complex dynamics of triple star systems. Triple star planets are an extraordinary example of celestial complexity. Some exoplanets are found orbiting within triple star systems, a rare and complex arrangement. These systems consist of 3 stars, bound together gravitationally, with at least one planet traveling through their shared gravitational pull. These systems are rarer than binary star systems, and the gravitational interactions between the stars and the planets are far more intricate. The resulting planetary orbits are not Keplerian, meaning they don't follow simple elliptical paths. Instead, they are influenced by the gravitational tug-of-war between the stars. A notable example of such a system is the KOI-5 system, where a planet orbits one star in the triple star trio. The primary star has a relatively stable orbit, while the other 2 stars orbit each other and the primary star. These distant companion stars affect the planet's long-term orbit. As a result, the planet's orbit oscillates, and its inclination and eccentricity change over time. Instead of a predictable circular path, the planet's motion is modulated by the interactions with the other 2 stars. Planetary formation in these triple systems is a complicated process. Protoplanetary disks, clouds of gas and dust from which planets are formed, may be disrupted by the gravitational pull of the companion stars. This disruption can prevent dust from clumping together to form planets. However, simulations have shown that planet formation is still possible in triple star systems, particularly when the disk is tightly bound to one star. Once planets form, their orbits are subject to gravitational disturbances, but these planets can prove resilient and dynamically stable, managing to survive these turbulent conditions. These triple star systems can also create unusual seasonal and lighting effects. Depending on the star's configurations, the planet might experience irregular day lengths, shadowing effects, or even multiple sunsets. Some planets orbit far from all 3 stars, only receiving faint combined light. Others orbit one star closely, while being perturbed by the other 2, creating a variety of potential climates and environments. These systems offer valuable insight into how planets can evolve in chaotic gravitational fields. Identifying planets in triple star systems is a challenge for astronomers. When looking for these planets, the light from multiple stars can make it difficult to detect the planet's transit or measure its velocity. Radial velocity signals, which measure the movement of a planet, can also be mixed with signals from the stars. Only with advanced technology, like high-resolution imaging and long-term monitoring, can astronomers begin to untangle these complex systems. These tools, now becoming more feasible with modern telescopes, help researchers better understand how these stars interact and how the planets behave within their gravitational field. One important mechanism in these systems is KOI lid-off oscillations, which cause large swings in a planet's orbital inclination and eccentricity. These oscillations can send planets into highly elliptical orbits or even lead to them being ejected from the system entirely. Some planets stabilize into unusual orbits that are far from predictable. These KOI dynamics play a key role in shaping planetary systems within triple star environments, and they remain a rich area for study. Despite the challenges of observing these systems, discoveries are becoming more frequent. Systems like WGR, which feature a young disk potentially forming planets in a misaligned orbit, hint at the wide variety of planetary architectures in the universe. Triple star systems show that planets are not limited to solar-like systems with one central star. Instead, planets can exist in many different orbital configurations, pushing the boundaries of planetary science. The astrobiological potential of triple star planets remains uncertain. While some of these planets may lie within the habitable zone of their stars, Their climate stability is questionable. The constant gravitational perturbations could lead to extreme seasonal shifts or even cause atmospheric collapse. However, these dynamic systems could also create unique environments that drive extraordinary evolutionary paths, offering a different kind of habitability. As technology advances, we are likely to discover more triple-star planets. Upcoming space missions, such as TESS and the Plato mission, aim to explore thousands of stars, including complex multi-star systems. Ground-based observatories using techniques like interferometry and adaptive optics will refine models of these planets' orbits and behavior. With these advancements, our understanding of planetary dynamics in extreme environments will grow, revealing new insights into the nature of planets in triple-star systems. Triple-star systems offer a new frontier in exoplanetary research. They highlight the resilience of planets in chaotic gravitational fields and challenge our models of planetary formation. As observational tools improve, more planets in these unique systems will likely emerge, further expanding our knowledge of the cosmos. Time itself behaves differently depending on gravity. General relativity. Einstein's theory predicts that time slows down near massive objects, such as black holes or neutron stars. This phenomenon, known as gravitational time dilation, has been confirmed both through experiments and in astrophysical observations. A clock near a massive body ticks more slowly compared to a clock farther away. This effect is a fundamental aspect of understanding space-time, as gravity is essentially the curvature of space-time itself. In areas with strong gravitational fields, such as near black holes, time dilation becomes extreme. For example, if an astronaut were to hover near the event horizon of a black hole, time for them would pass much more slowly compared to someone far away. From an external observer's point of view, the astronaut would appear to move in slow motion, but to the astronaut, everything would seem normal. This strange phenomenon is a natural consequence of the equations that describe gravity and space-time. Time dilation has been observed in everyday life too. For instance, satellites orbiting Earth experience time differently than clocks on the ground. Due to the weaker gravitational field at higher altitudes, the clocks on satellites run slightly faster than those on Earth's surface. If this discrepancy weren't corrected, GPS systems would lose track by several kilometers every day. This example shows how real and significant relativistic effects are in our daily lives. More extreme examples occur near neutron stars, where time dilation affects light signals. Pulsar timing measurements, for example, need to account for the time delays caused by gravitational effects. Even light signals traveling between parts of a binary star system are subject to these delays, which are used to test the predictions of general relativity with incredible precision. Time dilation also plays an important role in cosmology. As light from distant galaxies travels toward Earth, it passes through massive galaxy clusters. The gravity of these clusters bends and delays the light, a phenomenon known as gravitational lensing. The time delay in the light provides crucial information about the distribution of dark matter in the universe, helping astronomers map out the invisible mass that makes up much of the cosmos. Near a black hole's singularity, time dilation becomes so extreme that theoretically, time would stop at the singularity from an external perspective. However, this region is hidden behind the event horizon, making it impossible to observe directly. Understanding how time behaves in these extreme conditions remains one of the greatest challenges in theoretical physics. To fully grasp this, scientists may need a unified theory of quantum gravity, which merges the principles of quantum mechanics and general relativity. The effects of gravitational time dilation also have profound implications for interstellar travel. A spacecraft traveling near a massive object, such as a black hole, would experience time differently compared to Earth. This raises fascinating possibilities about time asymmetry in long-distance missions and introduces challenges for communication and synchronization. These relativistic effects must be taken into account when planning future space exploration missions. Even on Earth, gravity influences time. Clocks at higher altitudes run faster than those at sea level, a fact confirmed by atomic clocks in laboratory experiments. Though the difference is tiny, it serves as a reminder that time is not a fixed, absolute concept. It is, in fact, shaped by the environment around it. Gravitational time dilation is a cornerstone of modern physics, linking gravity, motion, and time in a unified framework. At just 2.73 Kelvin, slightly above absolute zero, the cosmic microwave background, CMB, provides a thermal snapshot of the early universe. This faint primordial radiation is essentially a fossil image from the universe's infancy. Small fluctuations in the temperature of the CMB correspond to variations in density in the early cosmos. These tiny differences played a crucial role in seeding the formation of galaxies and the large-scale structure of the universe. Modern missions like COBE, WMAP-ED, and Planck have mapped these variations with incredible precision. The data shows hot and cold spots, each on the order of millionths of a degree. These patterns are more than just temperature changes. They contain vital information about the universe's composition, its shape, and its age. The CMB spectrum closely follows the curve of a perfect black body, confirming its thermal origin. This rules out alternative theories such as the steady-state model and strongly supports the idea of cosmic inflation, a rapid expansion of the universe in its first few moments. Inflation explains the observed smoothness of the CMB, as well as the tiny anisotropies that scientists see. The CMB serves as a cosmic benchmark, helping cosmologists measure critical parameters such as the Hubble constant, matter density, dark energy, and the curvature of space itself. It's like a universal ruler and clock, providing an accurate measure of the universe's expansion over time. By studying it, researchers can test fundamental physics at energy scales that cannot be replicated on Earth. Polarization measurements of the CMB add even more depth to our understanding. These measurements trace the motion of electrons during the process of recombination and provide clues about gravitational waves from the early universe. Upcoming missions aim to detect B-mode polarization patterns, which could confirm inflation and offer insights into quantum gravity. The CMB is not just a relic from the past, it's a critical probe of the universe's earliest moments. To study it accurately, scientists must carefully remove any interference from our own galaxy. Galactic dust, synchrotron radiation, and free emissions from the Milky Way can obscure the faint CMB signal. By using sophisticated algorithms and multi-wavelength observations, scientists can separate these cosmic and galactic components, allowing for precise measurements of the primordial radiation. The study of the CMB continues to refine cosmological models, helping us understand some of the unresolved tensions, such as the discrepancy in Hubble constant measurements. These inconsistencies may hint at the need for new physics. Comparing CMB-derived values with other cosmic distance indicators has revealed gaps in our current understanding, prompting theories like evolving dark energy or exotic properties of neutrinos. Technological advances now allow for deeper and more precise observations of the CMB. Ground-based observatories such as the Atacama Cosmology Telescope and the South Pole Telescope complement space missions by focusing on smaller-scale structures and providing high-resolution data. Together, these observations offer a clearer picture of the early universe's physics. The cosmic microwave background is not just a faint glow in the sky, it is a direct connection to the universe's birth. It carries the thermal echo from the moment when matter and light separated, marking the end of the radiation era and the beginning of the matter era. By studying the CMB, scientists are able to explore the physics of the first moments of our universe's existence and continue to refine our understanding of cosmic evolution. Jupiter, the gas giant at the center of our solar system, is an intriguing planet. It emits more energy than it receives from the Sun, releasing about 1.6 times the energy it absorbs. This excess energy is generated by internal processes rather than solar heating. Unlike Earth and other planets that depend on sunlight, Jupiter's internal energy is a key factor driving its atmospheric phenomena. The source of this energy is gravitational contraction, also known as the Kelvin-Helmholtz mechanism. As the planet compresses under its own gravity, it releases energy in the form of heat. This process has been ongoing since Jupiter's formation, over 4.5 billion years ago. The planet continues to shrink slowly, sustaining its heat production over time. Another potential source of Jupiter's heat is helium differentiation. Helium may be separating from hydrogen in the planet's interior, sinking towards the core and releasing gravitational energy along the way. This process is supported by observations showing a depletion of helium in Jupiter's upper atmosphere. A similar mechanism is thought to be at work in Saturn. Jupiter's internal heat influences its complex weather systems. The Great Red Spot, the massive storm that has been raging for centuries, is partly powered by this internal energy. Unlike Earth's weather, which is driven by solar heating, Jupiter's storms are fueled by its own internal heat, enabling them to last for hundreds of years. The convection caused by this heat sustains these storm systems in the deep atmosphere. Jupiter's internal heat also affects its magnetic field, which is generated by the motion of metallic hydrogen in its core. This dynamic process creates an extraordinarily strong magnetic field, one of the most powerful in the solar system. Jupiter's energy also plays a role in its moons, particularly Io. The intense volcanic activity on Io is partly caused by tidal heating due to the planet's gravity. The gravitational interactions between Jupiter and its moons create additional dynamic processes, influencing the behavior of these moons. Europa and Ganymede may also have subsurface oceans, kept warm by these interactions. The Juno spacecraft, which orbits Jupiter, has provided unprecedented measurements of the planet's gravity and magnetic fields. These data have revealed complex zonal flows in Jupiter's atmosphere and have helped scientists refine models of the planet's thermal structure. Juno also measures microwave radiation to investigate atmospheric composition at various depths, enhancing our understanding of Jupiter's internal processes. By studying Jupiter's heat emission, scientists can draw comparisons with exoplanets, particularly hot Jupiters, gas giants found in distant star systems. These comparisons help us understand how gas giants evolve and how planetary interiors behave over billions of years. Jupiter's internal energy makes it more than just a massive planet. It drives storms, powers a strong magnetic field, and influences the behavior of its moons. The planet is like a giant furnace, glowing faintly in the infrared. This internal heat is not only what makes Jupiter a giant in size, but also a dynamic engine of planetary activity. For a long time, the Moon was thought to be a geologically inactive world, but data from the Apollo missions revealed that the Moon experiences seismic activity known as moonquakes. Between 1969 and 1972, astronauts placed seismometers on the lunar surface, which recorded different types of quakes. These included deep moonquakes, shallow quakes, thermal quakes, and those caused by meteorite impacts. These findings challenged the belief that the Moon's interior was completely inactive. Deep moonquakes, originating hundreds of kilometers below the surface, occur regularly and are tied to tidal forces from Earth's gravity. The Moon experiences stress from these forces, leading to periodic quakes. Although these quakes are mild by Earth standards, they provide valuable insights into the Moon's internal structure. Shallow moonquakes, on the other hand, are more intense and unpredictable. Some have registered magnitudes as high as 5.5 on the Richter scale and lasted up to 10 minutes. These quakes could be caused by tectonic activity, thermal contraction, or by adjusting fractures from past volcanic activity. Their strength and long duration suggest that the Moon's crust is under tension and may be brittle. Thermal quakes are caused by the Moon's extreme temperature fluctuations between day and night. As the surface heats up and cools, it cracks and produces small tremors. While these events are typically low energy, they are frequent and contribute to the gradual evolution of the Moon's regolith. NASA's Artemis program plans to deploy advanced seismic instruments on the Moon to monitor these quakes in greater detail. These instruments will map the sources of moonquakes more precisely and assess the risks they pose to future lunar habitats. The data will help us understand the Moon's long-term thermal evolution and its internal structure. Seismology on the Moon is essential for planetary science. It provides insights into the internal processes of a rocky, airless body like the Moon. It also contributes to our understanding of planetary formation. Moonquakes, like earthquakes on Earth, highlight the presence of internal stress and show that the Moon is not completely inert. By studying these quakes, we gain a better understanding of how rocky planets and moons evolve over time and how to plan for future lunar exploration. The concept of tiny black holes, also known as micro black holes or quantum black holes, is a fascinating and theoretical possibility. These objects were proposed by various models of early universe physics, and unlike stellar black holes, They didn't form from collapsing stars. Instead, they might have been created from extreme concentrations of energy during the Big Bang. Quantum fluctuations in the early universe could have led to the formation of incredibly compact regions of space-time, some of which might have been as small as atomic nuclei. The idea comes from applying general relativity at quantum scales. If enough mass and energy were concentrated into a tiny region, gravity would overpower all other forces, forming a microscopic event horizon. Some models suggest that these black holes could range from the size of subatomic particles to the mass of a planet. The formation of primordial black holes (PBHs) would have depended on the density and curvature of the universe in its infancy, right after the Big Bang. During the inflationary period, irregularities in density may have caused gravitational collapse in certain regions, leading to the creation of a population of micro-black holes scattered throughout the early universe. These tiny black holes could have played a significant role in the evolution of the cosmos and the formation of structure. Many of these primordial black holes might have evaporated through Hawking radiation, a theoretical process proposed by physicist Stephen Hawking. According to this, black holes emit radiation because of quantum effects at their event horizon. Smaller black holes would have evaporated more quickly, which means many of the primordial black holes might no longer exist. However, if some of these black holes were sufficiently massive, they could have survived until today, and their final stages of evaporation could produce detectable signals like gamma-ray bursts, high-energy particles, or even gravitational waves. There have been searches for these emissions using space telescopes and particle detectors, but so far no definitive evidence has been found. However, the absence of such evidence helps scientists narrow down the size and number of primordial black holes that might still exist. Some theories also suggest that micro-black holes could be created in high-energy particle collisions, like those in particle accelerators. If extra dimensions exist, gravity could become stronger at small scales, lowering the energy required to form a black hole. The Large Hadron Collider has attempted to detect these events, but no clear signs have been found so far. The theoretical possibility of stable, long-lived micro-black holes raises intriguing questions. Could they accumulate matter? Would they travel freely through space? Or would they become gravitationally bound to stars and planets? Simulations are being conducted to explore how these objects might behave. While their effects would likely be subtle, they could accumulate over time, potentially leading to noticeable consequences. Studying micro-black holes offers a way to probe the boundary between quantum mechanics and general relativity, two fundamental theories of physics. These black holes exist at the scale where both theories play an essential role, and understanding them could lead to breakthroughs in developing a unified theory of quantum gravity. Additionally, they provide a natural laboratory for exploring concepts like entropy, information, and the geometry of space-time. Although no micro-black holes have been observed yet, their potential role in early universe processes and dark matter continues to make them a priority for future research. Micro-black holes illustrate how extreme conditions in the universe could give rise to exotic structures that go beyond what traditional models predict. Another interesting discovery in space involves asteroids with their own moons. Asteroids once thought to be solitary rocks have been found to sometimes host their own natural satellites. The first confirmed case of this was Dactyl, a small moon orbiting the asteroid Ida, which was discovered by NASA's Galileo spacecraft in 1993. This discovery revealed that even relatively small bodies in the solar system can form binary or multiple systems. Ida, measuring about 31 kilometers in length, has a tiny moon, Dactyl, which is only 1.4 kilometers wide. Despite their size differences, they exhibit stable gravitational interactions, with Dactyl orbiting Ida at a distance of about 90 kilometers. This discovery challenged the assumption that only large bodies could host moons. It showed that gravitational binding can occur even in low-mass systems. The relationship between Ida and Dactyl also helped astronomers calculate the mass and density of Ida itself. The origin of moons around asteroids varies. Some might be remnants from collisions that created the parent asteroid, while others may be captured fragments or debris that coalesced into moons in orbit. In the case of Ida, Dactyl may have been a fragment ejected during an impact, and over time, gravitational forces stabilized its orbit. Since the discovery of Dactyl, dozens of binary and even triple asteroid systems have been identified, including near-Earth objects and asteroids in the main belt. Radar imaging, light curve analysis, and direct imaging techniques have all contributed to these findings. Notable examples include 243 Ida, 90 Antiope, and 87 Sylvia. Each of these systems provides unique insights into asteroid formation and the gravitational interactions between asteroids and their satellites. Observing the orbits of these satellites allows researchers to calculate the parent body's gravitational field, leading to more accurate models of its density and composition. Binary asteroid systems are especially valuable because they allow scientists to make measurements that are difficult or impossible with single asteroids. The presence of moons around asteroids also has practical implications for space exploration. Understanding an asteroid's gravitational environment is crucial for navigation and hazard assessment. NASA's DART mission, for example, targeted a binary asteroid system to test planetary defense strategies. By striking the smaller moon of an asteroid, scientists were able to measure how its orbit changed, providing valuable data for future efforts to alter the trajectories of potentially dangerous asteroids. The tidal forces between an asteroid and its moon can also cause surface stress, which may trigger landslides or changes in the regolith. These forces, along with the mutual eclipses of the asteroid and moon, create shadowed regions with varying thermal properties, which can contribute to the complex geology of some asteroids. Studying these binary and multiple asteroid systems helps refine our understanding of how small bodies in the solar system evolve. These systems can be analogues for understanding the processes that lead to binary star systems and other cosmic pairings. Future space missions aim to explore these dual systems in more detail. For example, the Hera mission will follow up on DART's impact with a closer look at the Didymos-Dimorphos system, providing high-resolution data that will improve our models of binary dynamics and the response of materials in such systems. The existence of moons around asteroids reshapes how we think about these small bodies. Far from being inert fragments, asteroids can host dynamic systems, with their own gravitational fields strong enough to maintain stable orbits. These findings continue to challenge and enrich our understanding of the architecture of the solar system. Lastly, Jupiter's surprising role in solar physics also offers an intriguing look at how planets can help us understand their star's internal structure. Solar oscillations, or pressure waves generated by internal solar activity, propagate outward and cause small but detectable motions on the Sun's surface. Light scattered from these oscillations reaches Jupiter, where its atmosphere interacts with these signals. By analyzing this reflected light, scientists can study the Sun's internal dynamics, an indirect observation method known as helioseismology by proxy. In 2021, researchers published results based on data from the SEMA instrument, which uses solar spectrometry to detect solar oscillations reflected from Jupiter. This technique revealed global modes of solar oscillation, allowing scientists to gain insights into the Sun's internal structure, including temperature, density, and rotation gradients beneath its surface. This discovery opened new possibilities for studying solar dynamics from distant vantage points. Jupiter's role as a mirror of solar activity offers a valuable method for remote solar sensing, supplementing direct observations of the Sun. This technique is especially useful when direct imaging of the Sun is impractical, such as during solar conjunctions or when spacecraft limitations prevent direct observation. By using planets like Jupiter or Venus to reflect solar oscillations, researchers can gain alternative perspectives that enhance our models of the Sun's behavior and improve our understanding of space weather forecasting. Any new method that enhances our understanding of solar modeling brings added value to the field. Jupiter, a gas giant usually studied for its own features, now plays a crucial role in helping us learn more about our Sun. Its reflective properties have become an unexpected tool in a technique called helioseismology. This innovation highlights how planetary science can provide insights into stellar physics. Jupiter's ability to mirror solar activity allows us to probe the Sun's hidden structure, offering a unique way to understand our star. In the realm of the fastest known stars, the pulsar PSRJ 1748-2446a stands out. This neutron star rotates at an incredible speed of 716 times per second, making each rotation take just 1.4 milliseconds. Located about 18,000 light-years away in the Tarzan 5 globular cluster, this pulsar challenges expectations of stability at such extreme speeds. Its rapid spin compresses space-time, presenting new challenges to current models of stellar structure. Pulsars are remnants of supernovae, extremely dense stars with masses greater than the Sun but confined to a sphere only about 20 kilometers wide. These stars have powerful magnetic fields that emit beams of radiation, much like a lighthouse. When these beams align with Earth, we detect regular pulses. PSRJ 1748 2446. Its extraordinary rotation rate was revealed through radio observations, which detected incredibly precise pulses every 1.4 milliseconds. This places it ahead of other millisecond pulsars, which typically spin between 100 and 600 times per second. The fact that this pulsar maintains its stability despite its speed raises questions about how it avoids falling apart. The centrifugal force it experiences comes close to the theoretical limit where it should break apart. For this pulsar to remain intact, its mass must be perfectly distributed to resist this force. Current estimates suggest that it might be slightly more massive than typical neutron stars. Its high spin rate is likely due to accretion of matter from a companion star, a process that gradually increases the pulsar's speed. This process, common in millisecond pulsars, has allowed this star to reach its extreme rotation. Despite its rapid spin, the pulsar remains stable, with its pulse timing remarkably consistent, indicating no imminent risk of structural failure. This suggests that the star's internal conditions are allowing it to endure the centrifugal forces. Studying PSRJ 1748 2446a helps refine our understanding of matter at nuclear densities, and it offers valuable insights into the elasticity and stability of neutron stars. Its rapid spin also causes the pulsar to become slightly flattened at the poles due to rotational bulging, which affects its gravitational wave emissions. While this particular pulsar has not yet been detected as a source of gravitational waves, its profile provides important data for future gravitational wave modeling. The dense environment of the globular cluster, Tarzan 5, where PSRJ 1748 2446 He resides, likely played a role in its evolution. Stellar interactions in such clusters are frequent, and a past encounter may have sparked the accretion phase. However, this also makes detecting the pulsar's signals more challenging due to the interference from other stars in the cluster. Advanced radio arrays are required to isolate these rapid pulses. The discovery of PSRJ 1748 2446 He pushes the boundaries of what we thought was physically possible for a spinning neutron star. If another pulsar were found to spin even faster, it would necessitate a revision of fundamental physics. For now, PSRJ 1748 2446 holds the record for the fastest spinning star. This pulsar's extreme regularity also has practical applications in timekeeping and navigation. Millisecond pulsars like this one are natural clocks used in pulsar timing arrays, with precision far surpassing even atomic clocks in long-term stability. These pulsars may eventually help detect low-frequency gravitational waves, offering even more insights into the universe's fabric. PSRJ 1748 2446 serves as a benchmark for rotational physics, compressing time into mere milliseconds. It acts as a natural experiment for studying centrifugal balance and nuclear matter. As detection methods improve, other pulsars with similar extreme speeds may be discovered, providing further clues about the properties of dense matter. Next, we look at TOE 4603b, an ultra-dense exoplanet that defies typical planetary classification. This planet, nearly the size of Jupiter, has a density greater than Earth's, suggesting an extremely compact internal structure. Discovered about 730 light-years away using data from the TESS mission, TOE 4603b is one of the most unusual exoplanets known. Most gas giants are low density due to their thick hydrogen-helium atmospheres, but TOE 4603b compresses a Jupiter-like volume into a far denser form. Its density exceeds 14 grams per cubic centimeter, more than twice that of Earth, which implies it has a massive rocky or metallic core, or perhaps it is experiencing extreme gravitational compression. TOE 4603b challenges our models of gas giant formation. Its high density and compactness suggest it might be a failed star or a borderline brown dwarf. Objects too massive to be classified as planets, but not massive enough to sustain hydrogen fusion. However, TOE 4603b falls just below the mass threshold for brown dwarfs. Its formation likely involved the accretion of heavy materials before acquiring a gas envelope, or it may have formed with this unusual composition from the beginning. The planet orbits its star in a short period, which places it in close proximity and increases tidal forces and internal heating. These extreme conditions could strip away lighter atmospheric layers over time, leaving behind a dense core. Spectroscopic studies of TOE 4603b reveal a hot, compressed atmosphere with an equilibrium temperature exceeding 1,500 K. Despite its size, the planet's compact nature contradicts the inflation typically seen in most hot Jupiters. This supports the idea that TOE 4603b's dense internal structure is the key to its unusual properties. Gravitational contraction and metal enrichment are likely factors at play here. The host star of TOE 4603b, also similar to our Sun but slightly more massive, may have influenced the planet's heavy element content, possibly creating a denser planetary core through a metal-rich protoplanetary disk. By measuring the planet's mass and radius, scientists were able to determine its surprising density. Transit data provided the size of the planet, while radial velocity measurements revealed its mass. These parameters allowed researchers to uncover the planet's extreme density. Such measurements require high precision and long-term observation. TOE 4603b is part of a rare group of super-Jupiters, which sit at the boundary between planets and brown dwarfs. The rarity of these objects suggests that their formation conditions are very specific. Studying TOE 4603b helps refine our understanding of planetary interiors, showing how extreme conditions can lead to novel compositions, such as heavy silicates, carbon, or even exotic matter. Future observations of this planet may test these hypotheses. TOE 4603b represents the outer edge of planetary diversity. Its dense and compact profile provides valuable insights into how extreme planetary environments can evolve. As new instruments detect more exoplanets, we are likely to uncover other ultra-dense giants, each expanding the boundaries of what we know about planet formation and structure. Lastly, the star HD 100006 7 hosts a rare and precisely synchronized planetary system. 6 exoplanets orbit this star in a gravitational resonance chain, where their orbital periods are related in exact ratios. This means that these planets align at specific intervals, creating a stable, predictable pattern. Each planet's orbit is linked to the others, creating a cascading synchrony, such as one planet orbiting 3 times for every 2 orbits of its neighbor. These resonant configurations are rare and indicate a gentle formation history, free from the instabilities or migrations seen in other planetary systems. The system, located about 100 light-years from Earth, is a valuable test bed for studying planetary dynamics. These planets are all sub-Neptune in size, with radii between 1.5 and 2.5 Earth radii. Their atmospheres are likely composed of hydrogen and helium, and their masses have been estimated using transit timing variations, which track small deviations in orbital timing caused by gravitational interactions. This allows researchers to estimate the planet's masses without needing direct radial velocity measurements. The discovery of the HD 100067 system reveals that planetary systems can evolve in a stable, synchronized manner. It contrasts with other known systems that show evidence of past instability or collisions. The planets in this system may have migrated inward through a protoplanetary disk, eventually settling into their resonant orbits. These synchronized motions provide a fascinating insight into how planets can maintain order over long periods. Much like the resonance seen in Jupiter's moons Io, Europa, and Ganymede, this system serves as an excellent model for studying how planetary systems evolve and remain stable. The resonance chain within the HDE 100067 system acts almost like a cosmic clock, helping predict future transits and assisting with long-term observations and characterizations. This rare and precisely synchronized planetary system offers a glimpse into the incredible precision of natural celestial mechanics. The 6 resonant exoplanets in this system orbit in perfect harmony, showcasing how gravity shapes and sculpts the universe. It's a remarkable example of how planets can evolve in a delicate balance, giving us a deeper understanding of the forces that govern planetary systems. Meanwhile, the Rubin Observatory is set to revolutionize our understanding of the dynamic sky. Equipped with the largest digital camera ever built for astronomy, the observatory will detect an astounding 1.4 million solar system objects annually. This includes asteroids, comets, trans-Neptunian objects, and more, all thanks to its 3.2 gigapixel camera, which enables rapid and extensive sky coverage. Located in Chile, the observatory will conduct the 10-year Legacy Survey of Space and Time (LSST), scanning the entire visible southern sky every few nights. With such a high cadence, it will track moving objects with unmatched efficiency, ensuring that nothing from near-Earth asteroids to distant Kuiper Belt bodies will escape its detection. Each image captured by the Rubin Observatory covers 9.6 square degrees, which is about 40 times the area of the full moon. The large size and sensitivity of its camera allow it to detect faint and fast-moving objects, making it an ideal tool for planetary defense. It will be able to map hazardous asteroids and monitor transient phenomena like supernovae, novae, and variable stars. Designed as a time-domain survey, the Rubin Observatory will document how the sky changes over time, tracking orbital shifts, spin rates, and even binary interactions. This vast data collection will allow the observatory to catalogue millions of previously unknown objects, expanding our understanding of the solar system's evolution. The power of the Rubin Observatory doesn't stop at solar system science. It will also probe fundamental mysteries of the universe, like dark matter and dark energy. By mapping the deep reaches of space, it will improve our understanding of galactic structure and cosmology. The data gathered will be processed quickly using automated pipelines with artificial intelligence and machine learning algorithms, classifying objects in near real time. Alerts will be issued for unusual events, enabling immediate follow-up by other observatories, allowing for a global response to discoveries. This collaborative project brings together institutions from around the world and will provide open access to its data, democratizing science and supporting both professional astronomers and citizen scientists. As part of its mission to study the solar system, the Rubin Observatory will make breakthroughs in understanding asteroid populations. It will likely double the number of known asteroids in certain groups, uncover new families, and monitor cometary activity. With its ability to track near-Earth objects, the observatory may even provide early warnings for potential impacts. The observatory's impact on solar system research will be immediate and long-lasting, as it opens new avenues for exploring the dynamic space around us. One of the most groundbreaking discoveries made with the James Webb Space Telescope (JWST) involves the detection of carbon dioxide in the atmospheres of planets in the HR 8799 system. This is the first time CO2 has been directly detected in multiple exoplanets within a single system. HR 8799, located about 130 light-years from Earth, hosts 4 massive gas giants, each several times the mass of Jupiter, orbiting a bright A-type star. Their large sizes and youth make them excellent targets for infrared observation, allowing the JWST's advanced instruments to isolate distinct atmospheric features. Carbon dioxide is a key marker of atmospheric composition, indicating the presence of a complex chemical balance. Its detection in HR 8799c and HR 8799e suggests these planets may share a similar formation history. Along with CO2, These planets' atmospheres also contain water vapor and carbon monoxide, with their ratios offering clues about where they formed in the protoplanetary disk. A high ratio of carbon to oxygen could indicate formation beyond the water ice line, a region farther from the star where ice accumulates and contributes to planet building. JWST's ability to isolate the CO2 sorption features in these planets' atmospheres is a testament to its precision. At 4.3 microns, the CO2 signals were clearly detected, allowing scientists to confidently assess the planet's atmospheres. These findings mark a significant step forward in the characterization of exoplanet atmospheres, and show that JWST's design is perfect for atmospheric studies of distant worlds. Though HR 799's planets are currently uninhabitable due to their extreme temperatures, the detection of carbon-bearing molecules like CO2 is vital for assessing the potential habitability of other, smaller exoplanets. This discovery tests atmospheric models under extreme conditions and refines our understanding of how different exoplanet atmospheres behave. HR 8799 C and HR 8799E, with temperatures between 800 and 100 K, have atmospheres shaped by strong vertical mixing, photochemistry, and cloud formation. Understanding how CO2 behaves in such environments offers insights into a wide variety of planet types, from gas giants to smaller rocky exoplanets. These 4 planets in the HR 8799 system provide a unique laboratory for studying atmospheric evolution. By comparing their similarities and differences, scientists can better understand planetary system formation. As more spectral detections are made, the growing data set will help refine our knowledge of exoplanetary science. The discovery of CO2 in multiple planets within one system is a major leap forward in the study of alien atmospheres, setting a precedent for future atmospheric surveys. The search for water has also led to compelling findings on Mars. Evidence suggests that ancient Mars once had vast oceans that covered as much as 20% of its surface. Topographic data, mineral deposits, and climate models support this theory, pointing to the presence of large bodies of water in Mars's early history. Features like shorelines, flood channels, and delta formations on the northern plains of Mars suggest that liquid water once flowed on the planet. These terrains are consistent with erosion caused by sustained water flow, indicating that Mars once had a more temperate climate capable of supporting liquid water. Radar and orbital spectroscopy have identified minerals like clays, sulfates, and chlorides, which are formed in aqueous environments. Their presence provides further evidence that Mars had stable liquid water in the past. The proposed Oceanus Borealis may have existed around 3.5 billion years ago, when Mars had a thicker atmosphere and higher surface temperatures. Volcanic activity and impacts may have triggered a transient greenhouse effect, allowing water to remain liquid on the surface for extended periods. Climate models suggest that with a denser CO2 atmosphere, Mars could have supported oceans and lakes. The source of this water likely included outgassing, comet impacts, and possibly subsurface reservoirs. Once released, the water may have accumulated in low-lying areas, particularly in Mars's northern hemisphere, where the topography is more conducive to ocean formation. Today, much of that water is either lost to space or locked in ice, with polar caps and subsurface ice sheets containing remnants of Mars's ancient ocean. Some of the water likely escaped to space, carried away by the solar wind due to Mars's lack of a protective magnetic field. Isotopic ratios of hydrogen provide clues to this loss, showing signs of massive evaporation. Mars rovers have further confirmed the presence of ancient water through sedimentary rocks, ripple marks, and vein structures, all pointing to past fluid activity. These findings help to paint a picture of a more Earth-like Mars, which raises the possibility that life may have once thrived there. Understanding Mars's watery past not only enhances our knowledge of the red planet's evolution, but also informs the search for life elsewhere in the solar system. Curiosity and perseverance have revealed layered deposits, suggesting that Mars once experienced extended wet conditions. This discovery supports the theory that Mars was more habitable in the distant past than we initially thought. The notion of an ancient ocean raises intriguing questions about whether life ever existed on the planet. Water is crucial for life, and a stable ocean provides the necessary time and chemical processes for prebiotic reactions to take place. If microbial life ever existed on Mars, it might have originated near these aquatic environments. Remnants buried beneath the surface may still preserve signs of ancient life. Mars's ancient oceans have completely transformed our understanding of the planet. No longer is it seen as a cold, barren rock. It once had vast bodies of liquid water. Determining where that water went and whether life emerged from it is one of the most important goals for planetary exploration. Future missions are set to uncover the secrets of Mars's buried past. The Milky Way galaxy is on a collision course with the Andromeda galaxy. This cosmic event, predicted to happen in about 4 billion years, will dramatically reshape both galaxies. Andromeda is currently 2.5 million light-years away and moving toward the Milky Way at a speed of 110 kilometers per second. Despite this enormous distance, gravity is pulling the two galaxies together, and their collision will significantly alter the structure of both. The prediction of this merger comes from detailed measurements by the Hubble Space Telescope and the Gaia Observatory, which have tracked the motion of stars in Andromeda's halo and revealed its path and velocity. This data confirms that the galaxies are on a direct collision course, not just a glancing pass. Over billions of years, the galaxies will begin to interact gravitationally and eventually merge. While individual stars are unlikely to collide directly due to the vast spaces between them, their orbits will be altered by the gravitational forces at play. The gas clouds in both galaxies, however, will collide and compress, leading to bursts of star formation known as starbursts. As the galaxies collide, their spiral arms will distort, and tidal forces will pull stars into long, sweeping streams and loops. The central supermassive black holes in each galaxy could eventually merge, producing gravitational waves strong enough to be detected by future instruments. However, their frequencies may be too subtle to measure with current technology. The entire process will unfold over billions of years, with the first interactions expected in 4 billion years, and full coalescence taking up to 6 billion years. After the merger, the resulting galaxy is predicted to take on the shape of a large elliptical galaxy, a dramatic change from the Milky Way's current spiral form. Although the Sun will survive the collision, its position within the galaxy will shift, potentially moving it to a different orbit or even into a galactic halo. Earth's fate will largely depend on the stability of the Sun, which may have already entered its red giant phase by then, making it uninhabitable. Computer simulations have visualized this entire process, showing how the galactic disks enter and mix. These models are crucial for predicting how stars, black holes, and gas clouds will behave during the collision. Observations of other galaxy mergers, such as the Antennae and Mice galaxies, provide real-world examples that help astronomers refine their predictions. The new galaxy formed by this merger is often called Milumeda or Milkdromeda. It will contain hundreds of billions of stars and could become the dominant structure in our local group. Over time, Milumeda will evolve into a more spherical shape as it settles, marking a significant milestone in the evolution of our cosmic neighborhood. The entire process reflects the dynamic nature of galaxies and the role gravity plays in shaping large-scale structures. Eventually, the local group, the cluster of galaxies to which the Milky Way belongs, will collapse into a single massive galaxy, isolating it from the expanding universe. The collision between the Milky Way and Andromeda is a slow, inevitable event that offers valuable insights into galactic dynamics, the merging of black holes, and the long-term fate of stellar systems. Although this is a distant event, its prediction highlights the impressive precision of modern astrophysics. Saturn, the least dense planet in the solar system, would float in water. With an average density of about 0.69 g per cubic centimeter, Saturn is less dense than water, which has a density of 1 g per cubic centimeter. If there were a bathtub large enough to contain Saturn, it would float. This unique property of Saturn is due to its gaseous composition. Despite its massive size, the planet is made up primarily of hydrogen and helium, which are light elements. Saturn's low density results from the lack of a solid surface. The planet consists mostly of light gases and has an immense volume, with a thick atmosphere that gives it its characteristic puffy appearance. Beneath this atmosphere lies a layer of metallic hydrogen and possibly a rocky core. While Saturn lacks a solid surface like Earth, its overall composition remains remarkably light compared to terrestrial planets. The comparison between Saturn and water is an effective way to understand its composition. Although the analogy is playful, it is scientifically accurate. Saturn's ability to float is defined by displacement. If an object displaces more water than its weight, it will float. Saturn, with its low density, would do exactly that in a sufficiently large ocean. This floating ability makes Saturn unique among the 8 planets. Jupiter, though also mostly hydrogen, is denser due to greater gravitational compression. Uranus and Neptune are also denser than Saturn, owing to their greater amounts of ices and rocks. Saturn's structure provides valuable insight into how gas giants form. The planet likely formed beyond the frost line, where lighter gases could accumulate. Over time, a core of heavier elements accreted a massive envelope of hydrogen and helium. Studying Saturn's density helps scientists model the formation of gas giants in other systems. This trait is often used to introduce students to planetary science, because the image of a planet floating in water is both captivating and educational. It connects everyday experiences with astrophysical properties, making Saturn a memorable and accessible topic in astronomy. Saturn's ability to float is more than just a quirky fact. It reveals much about its light, expansive structure and the processes behind its formation. In a solar system filled with dense rocky planets and massive gas giants, Saturn stands out as the least dense planet, and hypothetically, the only one that could float in an ocean. Planetary systems are born from galactic collisions. These events are not just destructive, they are also fertile grounds for new planet formation. When 2 galaxies collide, their gas clouds compress under the influence of tidal forces, which can trigger massive bursts of star formation. These new stars often form with surrounding proto-lunar disks of gas and dust, which can eventually coalesce into planets. As a result, galaxy mergers play a crucial role in the creation of planetary systems. Despite the dramatic appearance of colliding galaxies, individual stars rarely collide directly due to the vast distances between them. Instead, their gravitational interactions stir up the interstellar gas and dust, compressing molecular clouds that collapse into dense cores. These cores give birth to new stars and planets, and the entire process enriches the galaxy with fresh material. Some planets are ejected from their original orbits, while others are drawn into entirely new ones. Despite the chaos of galactic collisions, these disturbances create space for new planetary systems to stabilize. Over time, planets that form in these post-collision zones may become integral parts of a newly structured galaxy. Computer simulations show that galactic mergers lead to long-term changes in both star and planet populations. Stellar density increases in the cores of merging galaxies, while gas clouds are consumed in bursts of intense star formation. These dynamics spark temporary but intense waves of planetary birth, after which the new galaxy stabilizes and supports sustained star and planet formation. Exoplanet surveys have discovered planets in galaxies with recent collision histories. Although it's difficult to observe these directly, indirect evidence such as metallicity and age gradients suggests active planet formation is ongoing. Future telescopes may offer a clearer view of planetary disks in colliding galaxies. The Milky Way itself has a history of merging with other galaxies. Streams of stars in the halo of our galaxy trace back to ancient collisions. Some planetary systems in our galaxy could have originated from such events, and this will continue when the Milky Way merges with Andromeda in 4 billion years. Galactic collisions are part of a grand cosmic cycle, which may destroy older structures but also ignites waves of creation. In the aftermath, stars and planets are born from the resulting turbulence. These cosmic interactions are not merely violent, they are generative, producing the building blocks for future solar systems. The Sun itself did not form in isolation. Like most stars, it was born within a dense stellar cluster alongside hundreds or even thousands of sibling stars. These stars originated from the same massive molecular cloud approximately 4.6 billion years ago. Over time, gravitational interactions and the tides of the galaxy scattered the cluster. Today, the Sun's siblings are dispersed throughout the Milky Way. Evidence for this shared origin comes from studies of star clusters and simulations of stellar dynamics. Star clusters typically dissolve over tens to hundreds of millions of years. As the stars drift apart, they retain similar chemical compositions, allowing astronomers to trace their origins back to a common birthplace. The Sun's elemental fingerprint could reveal its siblings. Although finding these solar siblings is challenging due to the vastness of the Milky Way and the passage of billions of years, surveys like Gaia are mapping the positions, velocities, and compositions of billions of stars. By combining this data, researchers are identifying candidates that share similar orbits and chemistry. A few potential siblings have already been proposed, which may provide new insights into the early environment of our solar system. A dense cluster would have had a significant impact on planetary formation and the dynamics of the outer solar system. Nearby supernovae could have enriched the solar nebula with radioactive elements, potentially explaining isotopic anomalies found in meteorites. One theory suggests that a close stellar encounter early in the Sun's life disturbed the outer proto-lunar disk, which could explain the peculiar orbits of objects like Sedna. The dense environment of a stellar birth cluster increases the probability of such close passages, which may also support theories about the possible capture of distant bodies in the solar system. The size and density of the original cluster influenced how likely stars remained nearby. Larger clusters tend to disperse more slowly, while compact ones retain gravitational bonds longer. Some solar siblings may have joined different associations or moved to other spiral arms of the Milky Way. Tracking both motion and composition is key to detecting these stars. The concept of solar siblings is not just an exercise in stellar dynamics. It also plays a role in the search for extraterrestrial life. Planets that formed around stars with similar chemical compositions to the Sun might share similar environments. Studying these planets could offer valuable insights into planetary system evolution, raising the possibility that life could arise under similar initial conditions. Some stars exhibit remarkably similar compositions to the Sun, particularly in their elemental ratios. These matches are rare, suggesting that the original cluster has since dispersed widely. However, spectroscopic surveys continue to search for stars with compositions similar to the Sun. The emerging field of galactic archaeology is helping astronomers reconstruct the Sun's ancient stellar family. Identifying solar siblings provides a unique opportunity to understand the Sun's early motion, the shape of the original cluster, and its interactions with nearby stars. Each identified sibling refines our understanding of the Sun's formative years, bringing us closer to understanding the environment that shaped our solar system. The 2021 UEB is an exoplanet candidate, located at an extraordinary distance, near the outer limits of the Milky Way. This planet was detected using gravitational microlensing, a technique that reveals planets by observing how light is bent by gravity. The planet appears to be a lone object not clearly associated with a host star. Its isolation challenges conventional models of planetary formation and retention. Microlensing events are rare and require precise alignment. When a distant star passes behind a massive foreground object, the light from the background star is temporarily magnified. If the lensing object is a planet, it produces a unique signature in the light curve. This was the case with AT 2021 UEB, whose signal lasted just a few hours. Based on the observed magnification, the object is estimated to have a mass similar to that of Neptune or Saturn. It is located more than 20,000 light-years away, placing it near the Milky Way's outer disk or halo. No clear stellar signature was detected, suggesting that AT 2021 UEB might be a free-floating or rogue planet. Alternatively, it could orbit a faint, undetectable host star. Free-floating planets are believed to form in isolation or ejected from planetary systems. Gravitational interactions with other planets or stellar flybys can throw planets into interstellar space. Given its distance from the galactic core, AT 2021 UEB may represent one of these rogue planets. This discovery challenges conventional assumptions about where and how planets form. Most known exoplanets reside within a few thousand light-years of Earth. Finding a planet so far from the galactic center requires advanced detection techniques. Gravitational microlensing is ideal for this, as it doesn't rely on light from the planet or its host star. The discovery of AT 2021 UEB contributes to the growing catalogue of microlensing detected objects. These observations come from large-scale sky surveys like MOA and OGLA, and future missions like NASA's Roman Space Telescope will expand microlensing capabilities. They may be able to detect thousands of distant or free-floating planets. Studying a 2021 UEB helps refine models of the Milky Way's mass and structure. It suggests that planetary formation is not limited to the inner regions of galaxies, and planets can form and persist even in more sparsely populated environments. A 2021 UEB represents one of the most distant planetary detections to date, expanding the known range of planetary environments. Whether bound to a star or drifting freely, its existence highlights the incredible diversity of planets across the galaxy. Each new discovery like this pushes the boundaries of planetary science and reshapes our understanding of the cosmos. Interstellar clouds are vast regions of gas and dust where stars and planets are born. Although they appear silent in the vacuum of space, these clouds experience physical oscillations and turbulence. These wave motions occur in ionized gases and can be converted into audio by scaling electromagnetic or pressure wave data. This allows scientists to listen to the structure of the cosmos. The technique, called sonification, involves converting low-frequency vibrations into audible sound. The Perseus molecular cloud, observed by the Chandra X-ray Observatory, provides one such example. Pressure waves emitted from a nearby black hole caused oscillations in the gas cloud. When these oscillations were scaled up by 57 octaves, they formed a B-flat note 57 octaves below middle C. This sonification technique revealed deep, low-frequency tones embedded within interstellar structures. Sonification isn't just artistic, it has scientific value. By converting complex astrophysical data into sound, scientists can identify patterns and anomalies that might otherwise be difficult to detect. Just like images reveal the structure of the cosmos, sound uncovers variations in timing and frequency. This method has been instrumental in classifying gas dynamics and shock waves within nebulae. Additionally, it makes space data more accessible to visually impaired researchers. Each interstellar environment produces its own distinct sound profile. For instance, a calm molecular cloud emits soft, low-frequency oscillations, while a star-forming region has a more intricate pattern shaped by interacting forces. In contrast, supernova remnants generate sharp, transient signals that reflect the shockwave's propagation. These sounds, when translated, offer unique acoustic signatures for different cosmic environments. Sonification also plays a significant role in education and public engagement. By translating space data into sound, it allows people to experience the universe through a different sensory lens, beyond just images. NASA and other space agencies have created libraries of these space sounds, which include pulsars, planetary magnetospheres, and even the oscillations of our sun. This method acts as a bridge, making abstract physics more tangible and relatable. In star-forming regions, sound analogues can highlight early signs of instability. Clumps of gas that resonate differently may be early indicators of collapse, offering insight into where stars and planets are likely to form. This process, or rather sonification, helps visualize and understand gravitational fragmentation and turbulence. To gather high-resolution data from cosmic clouds, astronomers use instruments like ELMA and the VA. Often this data reveals hidden wave structures that, when transformed into sound, provide a fresh perspective on wave behavior and resonance within cold, diffuse gas. Sound adds a time-based dimension to spatial observations, offering a deeper understanding of cosmic environments. From molecular clouds to nebulae, the universe, when sonified, communicates through frequencies that we can hear, interpret, and study. Not all planets orbit stars, though. Some, known as rogue or free-floating planets, wander alone through the vast emptiness of space, away from any stellar influence. These planets may have formed in isolation or been ejected from their original systems. They exist in the cold, dark void between stars, emitting little to no detectable light. The discovery of rogue planets has led to a reassessment of what constitutes a planetary system. Rogue planets are detected using methods like gravitational microlensing and infrared observations. When their gravity briefly magnifies the light from a distant star, Microlensing reveals their presence. Infrared surveys, such as those conducted by WISE and Spitzer, have also detected some rogue planets based on their residual heat emissions. Although difficult to observe directly, simulations and indirect data suggest that billions of rogue planets may exist within the Milky Way alone. Some models propose that there could be one or more rogue planets for every star, suggesting that planetary ejection is a common occurrence. The violent dynamics of young planetary systems, particularly in their early stages, can throw planets into interstellar space. Rogue planets vary greatly in size and mass. Some are similar in size to Jupiter, while others are closer to Earth-sized or even smaller. Larger rogue planets retain internal heat for longer periods, potentially harboring subsurface oceans or atmospheres. Some may even have moons, adding complexity to their isolated systems. These free-floating planets, despite their isolation, may still be geologically active. Internal heating from radioactive decay or tidal stresses caused by captured moons could sustain subsurface environments, raising the possibility of habitability. Some theories even propose that life could exist on these dark, lonely worlds. Their existence challenges traditional definitions of planetary systems, which have typically centered around a star as the organizing force. Rogue planets defy this concept, existing independently and forcing scientists to reconsider planetary classification and formation theories. These objects occupy a gray area between planets, brown dwarfs, and minor substellar objects. The detection of rogue planets will continue to improve with future missions, such as the Roman Space Telescope. High-cadence microlensing surveys are particularly effective at catching rare alignments, which will provide more insight into how common these planets are and what their properties might be. As the number of rogue planet detections grows, we may even uncover new categories of planet-like objects. Understanding these rogue planets offers valuable insight into galaxy-wide planet formation models. They demonstrate that not all planets remain bound to stars, and their movements, distributions, and frequencies will help test existing simulation predictions. They play a crucial role in expanding our understanding of planetary systems and their life cycles beyond traditional starbound frameworks. Free-floating planets, though alone, are still part of the galactic ecosystem. Studying them gives us insight into planet birth, death, and survival in a way that defies conventional expectations. Their presence broadens our understanding of what constitutes a planetary system and challenges the traditional view that planets must orbit stars to be considered part of a system. At the heart of our galaxy lies a supermassive black hole known as Sagittarius A. This black hole, usually invisible in ordinary light, emits intense gamma radiation, which has been observed by the Fermi Gamma Ray Space Telescope and other instruments. This radiation extends over thousands of light years and signals high-energy processes occurring near the galactic center. The origin of this gamma radiation remains an area of active research. Gamma rays, the most energetic form of electromagnetic radiation, are typically produced by particle collisions, radioactive decay, or extreme astrophysical environments. The dense population of stars and the turbulent magnetic fields surrounding Sagittarius A make it an ideal site for such high-energy activity. One theory suggests that the gamma rays are produced by interactions between cosmic rays and interstellar gas. Accelerated cosmic particles collide with gas clouds, creating gamma photons. This hypothesis aligns with the observed distribution of radiation in the region. Alternatively, the black hole itself may play a role, either through past outbursts or ongoing accretion events. The galactic center is also home to the Fermi bubbles, vast structures of gamma radiation that extend above and below the galactic plane. These bubbles span more than 50,000 light-years and are believed to be remnants of high-velocity material ejected from Sagittarius A over millions of years. Some models even propose that dark matter annihilation could be responsible for producing gamma rays in this region. However, the observed signal profile does not fully match dark matter predictions, and astrophysical sources are currently considered more likely explanations. Millisecond pulsars in the central bulge of the galaxy may also contribute to the gamma ray signal. These rapidly spinning pulsars emit gamma radiation, and their combined emissions might account for part of the observed glow. However, distinguishing between the signals from pulsars and the diffuse emission from other sources remains challenging due to observational limitations. Recent high-resolution data from observatories like HESS and CTA have provided more details about the gamma-ray emissions, confirming the presence of complex structures and energy gradients near the galactic center. These findings suggest that multiple sources contribute to the gamma-ray environment. The gamma-ray landscape reflects the violent and dynamic history of the Milky Way's core, where starbursts, supernova remnants, and black hole flares have all played a part in shaping the region. Each of these events contributes particles, energy, and magnetic fields to the galactic center, creating a constantly evolving gamma-ray environment. Understanding the gamma-ray emissions from Sagittarius A** and the galactic core is crucial for refining astrophysical models. It helps us understand how energy is transported and transformed in galactic nuclei, offering valuable insights into black hole activity cycles and the conditions within the interstellar medium. These findings are not only relevant to our own galaxy, but they also have broad implications for other galaxies with similar central structures, deepening our understanding of the extreme physics taking place at the heart of galaxies. The radiation from the Milky Way's core serves as a powerful reminder that the center of our galaxy is anything but quiet.